great pleasure to, of course, Ursula Martin doesn't need any introduction. We all know her. She's an important computer scientist who can add to her surname many well-deserved acronyms that refer to her associations to and the awards that she received in her life. And she turned to, I would say, philosophy and history of computer science. And I know her for her book on Ada Lovelace, edited with Chris Hollings and Adrian Rice. And today, Ursula will give a talk on the past, present, and future of computer proof in pure mathematics research.
Thank you. Well, it's great to be here, and what a wonderful few months we've had, from icy cold in January to glorious sunshine in May. This is a talk about something I've been thinking about for a while, and it very much acknowledges the people whose work I'll be referring to, even if I don't always remember to say their names. So let's start with some fairly recent history. Last year, April and July, the bulletin, 2 editions of the Bulletin of the American Math Society, which is a volume of research articles sent to members, focused on the question, will machines change mathematics? Obviously, the underlying hypothesis was they might, or they wouldn't have bothered to have the volumes. And there was a collection of articles by eminent names in mathematics, in the applications of computers to mathematics, and so on. And this quote comes from the introduction. The introduction was by 8 mathematicians, 6 based in the US, 2 based in Canada. Pure mathematicians are used to enjoying a great degree of research autonomy and intellectual freedom, a fragile and precious heritage, which in slang English one calls clutching one's pearls, that might be swept aside by a mindless use of machines. Well, I mean, you could spend an entire hour unpicking that. Mindless, lacking less of who's, mindless by whom? That's not grammar, but, and so on and so on. Now is the time for mathematicians to learn about and then drive this debate and decide upon our subject's future direction. And this came against the background of experiments like this, which are even more recent history. About 6 months ago, a company called Epoch AI published a press release, accompanied, of course, by a paper on the archive. The press release quoted Richard Borchard's Tim Gowers and Terry Tao in PR for something they called Frontier Math, which was a problem set to compare mathematical software based on AI. Richard Borchard's Tim Gowers and Terry Tao are winners of the Fields Medal, which not only shows tremendous accomplishment in mathematics, but means that they and other holders of the Fields Medal are often invited to validate, if you like, activity by making, statements about it. There's quite a long article which is summarized by saying mathematicians, i.e. them, anticipate AI will change math research by enhancing proof development, generating novel conjectures, lowering entry barriers, and all good stuff, Epoch AI can afford a good journalist. So what was the paper all about? Well, it reported on what's called a benchmarking competition, which is quite common in AI. When you've got lots of different AI systems, AI companies are all competing with each other. And so you have problems where you set challenges and you see which system solves the challenges fastest or gives the best answers or whatever it might be. The 7th of November 24 paper suggested that the best system in their competition solved 2% of the problems. Now that doesn't sound very good until you see what the problems were. The problems were provided by senior members of the mathematical community. Now, well, if you read that, what's it asking about? It's asking about recurrence relations, but recurrence relations with hideous big numbers in, so probably your first instinct is to go away and try and factorize those numbers, see if anything interesting is happening. Recurrence formula with initial conditions. Now, it's not asking you to prove something, it's asking you to find a number. Find the smallest prime p congruent to 4, blah, blah, blah. Why is it asking you to find a number? Because actually, if you're having a competition, asking the system to find a number, it's much easier to judge the competition than if you ask the system to give a proof where you have to read through the proof, which might or might not be right. So you ask it to give you a number. Well, how might you solve that problem? Well, if you're somebody who knows an awful lot about recurrence relations, you've probably got a bunch of different things in your head about different theorems and so on. You've probably got, if you're lucky, you've got a bunch of different things in your head about analytical p-adic fields or something. And if you're lucky, you know, you connect them up. And the idea of these systems was that they were essentially ChatGPT for maths. They have hoovered up an enormous amount of mathematics, all that stuff that we generously put on the archive or on our web pages or provide as exercises for our students. And they, using this ChatGPT-like approach, which I'll say a little bit more about later, they can indeed put lots of different statements together and, with luck, come up with answers. Well, 2% doesn't sound too good until about a month later, when it was announced that OpenAI's O3 had achieved 25%, which is better. But then you see the problem started. The archive paper was, the earlier one, was updated to clarify, which, as you know, means, oh my goodness, we've been caught out doing something bad here. To clarify that Epoch AI is funded by OpenAI, and OpenAI had exclusive access for training purposes to most of the hardest problems and their solutions. So, strong implication that OpenAI had seen the exam beforehand, or, you know. If you haven't heard of OpenAI, this is the company behind ChatGPT, which is, you know, why it has a lot of the technology it needs to do a ChatGPT for math. It was founded by some guy called Elon Musk. Anyone know what happened to him? And somebody else called Sam Altman. If you follow the news on this, all the stuff on this, is not one of the world's nicest people either. And it's being recorded. It was founded by them. Musk then pulled out. They've been hugely controversial for many, many reasons. Musk is now trying to take it over again. I've actually lost track, but anyhow, we've jumped from solving pure maths problems into the world of AI politics. So I'm going to talk about this world. I'm going to go back a bit and talk about computation in pure mathematics. I'm going to talk a little bit about formal proof by computer and large language models for maths. And in case I forget to say it at the end, I mean, what we're seeing here is an interplay between mathematicians, big tech, government. We're seeing all kinds of ways in which people are being, organizations, institutions are being used by other organizations or institutions in ways they might not have expected. We're seeing all kinds of conversations that perhaps the math community is not used to having. When we're thinking about mathematics in this kind of discussion, we're generally thinking not about all this lovely stuff up the side, the kind of thing we were just hearing about, climate science. We're interested in this bit, talking about this bit in the middle, pure mathematics, and the kind of elite status that holds in the mathematical world. We're talking about a world in which the outputs of pure mathematics are still, after several hundred years, the traditional mathematical paper, epitomized by papers in the UK's Royal Society from whenever the Royal Society was founded. Well, I don't know. Somebody knows. And we're seeing a massive growth in mathematics publications. If you can't read the caption, the massive growth, this was taken from something that was meant to, in 2022, was meant to be showing US decline, but possibly it's been repurposed in present politics. But the massive growth is in the blue line, which is China, and the brown line, which is the dark brown line, which is India. And we're talking about what you might call a stakeholder ecosystem. We're talking about all the people involved in producing that mathematics, the people in institutions, the researchers, the educators, the students, the employers, the publishers, the institutions. And we're talking about concepts that people talk about, well, how does somebody get credit for their work by publishing a paper that's attributed to them, that contributes to their reputation, that contributes to their employment prospects? The significance of what they're doing is judged by all kinds of social processes, and there are people who've spent a lot of time thinking about social processes. This is a picture taken in the Punter at another Newton Institute workshop a few years ago. The Punter's the pub over there, if you haven't discovered it. People hard at work, collaborating. I know it because of the hands. There are no women in it, except me, but I took the picture. And people have spent time understanding what's going on in these informal human processes. Michael wrote a paper about chalk, where he talked about how much effort it takes to understand a paper, to work out what's going on. And advanced mathematics needs that understanding, it needs that disorder, that messing about, that's the perception from ethnography of mathematicians, anyway. Or someone called Lorenzo Lane observed mathematicians collaborating here and pointed out how much work goes into, you have an initial idea, you spend a lot of time thinking about how best to formulate it, what's the structure of lemmas, you spend a lot of time sharing that to build support and exchange ideas. And those informal processes are what feeds into how mathematicians develop these ideas of significance. I'm not really talking much about that, I'm just thought they'll pop up again later. But the stakeholders, once you start thinking about the digital, the stakeholders include, well, basically if you're using digital stuff, it costs money and it has to come from somewhere. So the stakeholders include the funders, they include government who are grant givers, they include the tech companies. And that starts to create a different kind of dynamic. And we're starting to think about what one might rather grandly call digital infrastructures. Well, you know, we're all familiar with these things like the archive or Google Scholar or LaTeX. You know, they come from somewhere. They don't just magically pop up on your laptop. They've come from somewhere. Someone's made them. Someone's looked after them. Someone's made decisions about them. Math Overflow published platforms or software like MATLAB or Maple or indeed O3, which was ChatGPT for math. And when we're thinking about those, there's a kind of framework that's used when people are thinking about technological innovation more generally. And I just want to illustrate it with the example of a very simple digital infrastructure, the online encyclopedia of digital sequences. Now, if you don't know that, that's a web page. You go and you type in a sequence of numbers, you hit search, and if you're lucky, it knows about it. And it tells you what the sequence is, what the further members are, and of course it gives you references, so you can find out more about it. It gives you links to other sequences. It started off actually as a, does anyone remember the big paper book written by Neil Sloan? Well, it started off as a paper, artifact. Now what happens if you think about that as a digital infrastructure? Well, someone's designed the thing. Someone's made the decision that you just go to the website and type in some numbers. You don't have to have a password. You don't have to identify pictures of traffic lights, you know, none of that. Someone's thought about not just designing it, but sustaining it so that it works on, I think it works on your phone, you know, it works on many different kinds of browsers. They thought about how to keep it going. You know, the web is full of dead things, which were a bright idea. We've heard about several of them this week, which were a bright idea at the time, but are there no longer. They thought about the data. They thought about accessing it, curating it, the data. I mean, there's a huge, it's quite, what's going on at the back, which I won't really talk about, is pretty sophisticated. And it's got more and more sophisticated over the years, because you're not just matching the sequence to exactly that sequence, you're matching it to various transformations of the sequence. So there's a kind of mathematical infrastructure at the back. There's a whole lot of questions around accountability, provenance, and trust. You trust that these references are correct. How do new sequences get added? Well, you could submit a sequence, and there are people who, there's a whole maintenance task of making sure that the sequences are still there, making sure that the sequences are right, making sure that you're, you know, you're giving credit to the right paper for them, and so on. And then, of course, as I said, it costs money. There's governance. Who do you complain to if it's broken? Well, that writing's right up at the top in a small font. It says, supported by donations to the OEIS Foundation. So it's a foundation. It's got a board who are named, who ultimately are taking responsibility for this thing. There's an awful lot of volunteers doing work under the hood. It's a sort of Wikipedia format. Money comes from the foundation and so on. And to think about an infrastructure, you need to kind of think about that kind of thing. And we've, you know, we can all think of infrastructures that have broken. June mentioned one yesterday. I forget which it was, but it was a... Queen Victoria's Diaries. Queen Victoria's Diaries. Well, I don't know, was that a victim of the hack of the British Library? Was that a victim of the fact that it just didn't get updated for new browser technologies? Sometimes things go for commercial reasons. Google Scholar, we're familiar with. There used to be a Microsoft Scholar. I've even forgotten what it was called, but there was a Microsoft version. It's not there anymore. Presumably Microsoft decided, you know, it wasn't commercially viable to carry on running it, which was a bit unfortunate if you built lots of other stuff on top of it. So that's the kind of framing for these things. But now if we go back and think about, well, electronic computation in pure mathematics, you know, if we went back to the abacus, we'd be there all day, so I'm not. Let's go back to the archives of the Royal Society. And a grant proposal from Max Newman. Max Newman was a mathematician in Cambridge who was very instrumental in what went on at Bletchley Park, then moved to Manchester and was involved in setting up the early Manchester computers. And this is a grant proposal he wrote to the Royal Society in 1946. There are tantalising things missing from the Royal Society archive. Obviously, he didn't kind of just ride up to London on his bike and drop it off from cold. Obviously, you know, one has to assume that there'd been a lunch at a club and he'd been, you know, hey, old boy, if you submit this, you know, money will come. So he submitted the grant proposal. It was refereed by his best mate, that tends to happen, Hartree, who was involved in early computers in Cambridge. It's rather hard to read, except perhaps in this bit, in the referee's report, you can just see group theory, topology, Poincaré hypothesis, four-color problem, Riemann-Zeta hypothesis, and so on. But if I make it more legible, Oh, hang on, I lost a slide. Oh, sorry, I did mean that. They got permuted. So what he's essentially trying to do, I learned about this from a paper by Simon Lavington, a historian of computing based in Essex. What they were essentially trying to do was build the top secret machines they built at Bletchley Park again. And so the proposal refers to in the war I saw this and that, which is code for, what it's code for. I know that we were all at Bletchley Park, but I'm not allowed to talk about it. But he's talking about, well, the setting up and the machine of the same operations every time is a bit tedious. So let's make standard logical parts, reusable code, before people had code, but it's not clear if he was thinking about standard logical hardware or standard logical sets of instructions at this point. And it'll bring the ideas of symbolic logic and abstract algebra into the field. There is also a retroaction to be expected on these fields in pure mathematics. So he makes the case for this funding by the contribution that this machine will make to pure mathematics. Now, what we don't know if that was just a show, or if that was the real motive, but because we still don't have access to some of the archives. But what would the value of such researches be for pure mathematics? That they might, in some cases, produce a counterexample. That near misses might give insights into the obstacles to a proof. The experience in handling problems of a non-numerical type would be useful. Hartree, in his best mates referees report, talks about group theory, topology, testing out the Poincare hypothesis, the Riemann-Zeta hypothesis, symbolic logic, and so on. One of the reasons, for example, for choosing group theory was people had already been experimenting with pencil and paper algorithms for group theory. Newman himself had. Well, the results of that investment, another investment in computers in the UK, was shown off in 3 computing conferences in 1949, 51, and 53. One here in Cambridge, and you saw, if you were here, whenever it was a few weeks ago, we all went down to the computer lab. You saw bits of the computers. One in Manchester in 51, and one at NPL near London in 54. Already, well, sorry, this is slightly later, this is 64, but already computing companies were using their work in mathematics, were using the fact that computers were being used by mathematicians to sort of validate what they were doing, to give legitimacy, to give luster to what they were doing. This is actually an ad from IBM of Courant and Goldstein. I'm sorry, I see what's happened. I've accidentally deleted the slide. However, that's why I'm going, yeah. I've accidentally deleted the slide that says that in these Manchester conferences, there were papers reflecting this work on number theory and work on group theory. Work on number theory was particularly prime sieves. Now, the papers are just one page saying, we did this. They totally hide the huge labor of doing it. Remember, this was when some of the early machines were programmed by literally plugging things in. Some were programmed by paper tape, but they just report, well, using the machine, we've investigated Mersenne primes, or using the machine, we've investigated groups of prime power order, actually groups of 2 power order, because you could use clever coding tricks to encode 2 groups with those binary strings. And group theory is one of the places in pure maths where you see this research playing out earliest. This is from 1961, so only 10 years after these conferences. This is a paper by Ken Appel at Urbana-Champaign, Marshall Hall at Caltech, and John Thompson at Harvard. And this is part of Veit and Thompson's investigations of finite simple groups. White and Thompson went on to prove the odd order theorem, that all groups of even order are soluble. But at this stage, they haven't proved it yet. They've only proved it in certain special cases. And Marshall Hall, who's the guy with access to the big computer, the Institute for Defense Analyses, i.e. the government, has given a computer to Caltech to do whatever. But Marshall Hall is picking it up to use it for investigations of group theory in 1961. And that tradition continued with work in group theory. Big problem in Oxford, conference in Oxford in 1968. I'm sure it was 1968. I can't see the date on it. But here what they're doing again, Marshall Hall reporting on the discovery of one of these sporadic simple groups, the Yanko group, one of the Yanko groups. What had happened was that Yanko had said, if this group exists, it has such and such properties, and so they conducted a search for a bunch of matrices which particular properties that would generate the group. The construction was carried out, in August 67 at the University of Warwick, which had only just got started. And at Cambridge University, Mr. Peter Swinnerton Dyer, who was later a rather eminent academic and academic politician, was helpful at writing in short notice a program for the Titan computer, which finally confirmed. When we went out to the computer lab, as you go in on the left, you can see an old piece of computer, rather fine piece of computer hardware. That's the Titan console, and it talks about Peter Swinnerton Dyer. So computation got embedded in group theory, the practice of group theory, quite early on. Its manifestation today is a system called GAP, which you can looked after by the University of St Andrews. GAP was put together with contributions from Joachim Neubius at Aachen and John Cannon in Canberra. And what they were doing, they were doing what Newman was talking about. They were pulling together libraries of code that people could reuse. And Neubius, very early on, before really people were talking about open source, what he was saying was, this is going to be open source. Mathematics, information is passed on free of charge, and everything is laid open for checking. Therefore, a fundamental principle of this thing has to be not applying these rules means moving in a most undesirable direction, he said. And so that meant he wanted it to be built and maintained by the group theorists rather than it becoming a commercial product. And that meant that if you phrase it in terms of digital infrastructures, he had to think about all this stuff. I won't go through all of it, but one of the important things, for example, was sustaining the community. And so the early group theory conferences very often have lectures by Neubius, or they have demonstrations of use of the software. He was also thinking about, they were thinking about all these things. But one of the things they were thinking about was, it's all very well if you want, expecting academics to write code for this, but they have to get, if they're not publishing papers, they have to get credit in some other way. And they thought about various mechanisms which manifest themselves today in the fact that if you submit something for this library, it's given a DOI. So it's, it counts as a publication. Yes, and when you look at how this system has become embedded, well, the people maintaining it, very often they'd rather like to know who's using it. And they ask people to cite it, but people often don't. So they have to, they tried sampling just to see how people were using it. Explicit computation as part of a proof, generating examples and counterexamples and so on. But quite often, its use wasn't really acknowledged at all because people were using it to doodle about with, like you'd use a calculator or something, but there wasn't something that you could fit into the formal narrative of the papers how it was written, so they didn't. There's no reason to particularly. Well, that was a probably non-controversial example of the use of computers in proof. The example that everybody's heard of is the four-color theorem. The computer proof of the four-color theorem. Every planar map can be colored with four colors. Well, if you look at that map of Wales, you see it's got rather more than four colors, but if you changed all the purple into something, that lime greeny color, you got rid of one of the colors. So that was the problem. It was a problem since the 19th century. In 1976, Appel, that's the same Appel, announced a proof with computer assistance. It was huge. It was 400 pages of hand analysis plus computer colouring of 1,834 maps of Wales, or 1,834 special cases. And that was what started to generate discussion in the mathematical and philosophical community about the use of computers in proof, which is a different thing, I think, from saying it was especially controversial among the people closest to it. But the philosophers picked up on this. Timoshko published a rather strongly worded, what's the word I mean, polemical philosophical piece. Later on, a journalist called John Horgan wrote a piece in the Scientific American called The Death of Proof, which really pissed off the mathematicians, because after all, the policymakers might read the Scientific American. You don't really want the journalists saying that mathematicians are all redundant, do you? There's a very detailed study of it in Donald Mackenzie's book, which covers many of these issues. And if one goes back and reads Donald's book, it is a very careful and detailed analysis. And people use it as evidence of a controversy among mathematicians. It's not actually that, it's evidence of a controversy among sociologists of science. And the book, and even more the papers that feed into it, are quite specialized discussions. It's an interesting shift of perspective somehow. Well, and that was one side of things, the use of computers in mathematical practice in various ways. And, oh my goodness, I need to speed up. But the other side was this thing that Newman was talking about, the search for standard logical parts out of which instructions could be built up and so on. Has already brought out the ideas and methods of symbolic logic. Newman was a topologist working in Cambridge. He's also spent time in Vienna working with logicians, and he actually lectured in Cambridge on the work of the Vienna School and introduced Turing to it. It's not clear what exactly he was thinking about there, but if you turn to one of the Cambridge Computer Conference in 1949, here's a paper by Turing called Checking a Large Routine. Well, actually, he says in a sort of deadpan Turing way somewhere near the beginning, well, you know, it's not really practical to check a large routine in this paper, so I'm just going to check a small one. And the paper is very hard to read, partly because he's using weird notation and partly because the typesetter left out all the subscripts and superscripts. So, but his basic idea is, think of a program with a flowchart. Then if you look, for example, at this box here, this diamond, that's a conditional. If the value in the box is rated as positive, you do something. Sorry, if it's negative, you do something. If it's 0 or positive, you do something else. If you go down the negative branch, so before the diamond, this is true. If you go down the negative branch, the thing up the top, which I can't reach, is true. If you go down the other branch, before you do it, this is true, and after you do it, this is true. So you're sort of reasoning about the program by saying, okay, if you do this, if you start with variables like this, and you do a thing, the variables become another thing. These ideas emerged from a number of people. There's a whole other literature on exactly where the ideas came from and so on. But the idea being that you could use formal logic to think about programs. And the example I just gave becomes a logical rule for talking about a conditional. And then you can do a proof. You can say, okay, suppose you know that if x is greater than or equal to y, the maximum of x and y is x, bit over y greater or equal to x, then by that rule there, it follows this. You can do inferences about programs. You can reason about programs. And so that you can reason about programs. You can write down formal proofs that are about programs, just as Principia Mathematica writes down formal proofs that are about numbers. Well, that idea gained huge traction, actually, in the 60s and 70s. A great literature on different kinds of logics. It was, this is another conversation, I've got to get to what I'm trying to say, but why did it emerge and why did it become so popular? It's an instance of modernism, which we were hearing about earlier. A huge variety of computer systems. Katya has touched on some of this in her talk. But what emerged was huge academic investment and industrial investment in certain places where it was found useful. So in the 1980s, Intel had a spectacular failure with a bug in their new Pentium chip. And you could trace the bug down to the fact that when they were in the code that built the chip, a thing here was meant to be just copied to there, but it wasn't. They lost a number off the end. So it wasn't a deep, subtle mathematical issue. It was just, you know, a piece of, but so that led particularly to investment in how you write down a logic for reasoning about computer chips. Well, one of the things that computer chips do, of course, is calculation of you don't calculate trig functions in software, you calculate them in hardware. So you had to have algorithms for proving property, you had to prove properties of trig functions. Well, this became a huge business and hugely controversial, partly because other computer scientists were rather fed up with the curriculum getting full up with logic. Even if this was so, we would still insist that verification renounce its claim on all other areas of programming. To teach students in introductory programming courses how to do verification ought to be as far-fetched as teaching students in introductory biology how to do open heart surgery. Well, he was on a roll. But he kind of had a point. I mean, these were specialist techniques that worked for toy models of programs. They didn't work in the practicality of how big computer companies were building software. But the software programs were written, and so people started to experiment with them just to do mathematical proofs. So if you're sitting in front of the whole system I mentioned just a moment ago, designed to prove properties about chips, supposing you want to prove the Jordan curve theorem, do a formal proof of the Jordan curve theorem, what do you have to do? Well, you have to choose some software, and you might be thinking about all those infrastructure issues. Do I trust it? Is it going to be there when I finish what I'm doing, or is it just a student project that's going to get thrown in the trash? You have to select how you're going to formalize the Jordan curve theorem. Well, that actually involves a lot of the informal processes I mentioned before. How are you going to formalize it? You write it out in great detail. You then have to, think of doing how Russell and Whitehead might have done the Jordan curve theorem. It would take them pages and pages and pages. And you do all that. You type it into your computer system, and your computer system is going to check every line of the reasoning. Your computer system really is generating a formal proof. It's not doing it by you typing in line by line, which is what Katya was showing us in the first talk. It was doing it by having macros that would check a lot of things at a time, because this wasn't teaching you computing, this was just trying to get the job done. So that led to a big development of this kind of software. And mathematicians starting to think seriously about it. Maybe the most striking one was Tom Hales and his proof of the Kepler conjecture. The Kepler conjecture says that if you stack up cannonballs or tennis balls, then the most efficient way to stack them, i.e. with the fewest spaces between them, is the way you might think in a pyramid. He had a hand proof which depended on a particular murky inequality. So, and the referees were rather uncomfortable about this. So Tom Hales, who of course had tenure and you know, wasn't going to take this lying down, decided to go away and check his proof in some of this theorem proving software. Now, it was a huge effort. If you look at the dates here, paper received 1998, revised, accepted, published online 10 years later. It's a huge effort. And that's one of the problems with this. It is a huge effort. The paper has credits. If you look at the credits, well, there's Tom Hales, who was in charge. There's the software that came from Intel, and some more software came from a group here in Cambridge. You've got people doing line by line, masses of detailed logical work. You'll see a lot of names here that look Vietnamese, because they are Vietnamese. Tom got an NSF grant and managed to maneuver the politics. We are talking late 90s, to spend that NSF grant in Vietnam, where it would buy him a lot more hands, and gave courses in Vietnam, so as to have a whole bunch of people ready to do the work. But he did the work, and the journal was accepted and not seen as very controversial. The descendant of that is a software system called Lean. There's a great deal of work now going on. Lean was used by the Fields Medal winner Peter Scholze. If you're a non-mathematician, you may be puzzled by this way mathematicians have of prefixing people's names by Fields Medal winner so-and-so. You know, like Olympic athlete so-and-so. It's a sort of convention. You say, Fields Medal winner Peter Scholze, you see. So what this did was it tried to cut down the time. So rather than taking 10 years, which is somewhat impractical, even if you've got tenure, to see if that could be done sort of in real time. Well, it could be because there have been many technical advances in how to build these things and how to deploy them. Someone called Kevin Buzzard, who's at Imperial College, is really devoting himself to doing, I think, very much what Joachim Neubuser did for the group theory community, what Newman said he was going to do in his grant proposal for the initially, to put together all the ingredients you'd need, pre-prepared lemmas, if you like, pre-prepared chunks of proof, so it would be easier to use these things. He now has a major grant proposal from the UK, from the UK Funding Council, to do this. And so, if you like, what he's doing is taking all this experimental work on Lean, on getting computers to produce formal proofs, and putting it in some version of this kind of framework, you know, including making sure that people can get credit. Well, one way people get credit is having worked on this for a while, they go off and get very highly paid jobs in tech companies. But another way is, you know, that they can get credit by having CV-worthy activities and all those other sorts of things one is doing which are not technical. Well, I need to speed up. And I need to speed up to talk about large language models in in pure mathematics. Well, I guess everyone's heard of ChatGPT, right? So in the course of preparing this talk, I didn't really know much about Max Newman and the four-colour theorem, but he'd mentioned it in his grant proposal, or his referee had. So, of course, I did what anybody would do. I asked Google. And Google's AI overview told me, well, what did it say? It said Max Newman was a Cambridge mathematician, true, has significant influence on the development of computation. Well, discuss what you mean by computation, but, you know, it's not that wrong. And the study of the four-colour theorem. Well, he kind of mentioned it. Actually, you know, when you look at this, it's fairly obvious that Google's AI system has ingested that paper by Simon Lavington. It's probably ingested Andrew Hodges' biography of Turing. He is credited with, by whom, you know, red ink in the margin, introducing Turing to the four-colour theorem. Well, he might have done. I mean, you know, he and Turing overlapped in Cambridge, and he was, so who knows? Which later led to Turing's work on the Turing machine. What? And the contribution of computability. Newman envisaged using machines like the Turing machine for pure mathematical working. But see, the interesting thing about that is, if you cut out all the gratuitous references to Turing, it's not that wrong. You know, it's not perfect, but it's not that wrong. And what that's showing you is, you know, I introduced it as a joke. It did, incidentally, find me a letter in the St. John's archives from from G.H. Hardy to Max Newman, saying something along the lines of, I can't parody Hardy exactly, saying something along the lines of, hey, Newman, I've got another crank proof of the four-colour theorem here. I know you're really good at spotting errors in these things. So, what do large language models do? They ingest vast quantities of text, you know. All that mathematics we have so thoughtfully and generously put on the web, everything we've put on the archive, everything you've written in, possibly not everything you've written in a referee report, but everything you've written on Stack Exchange, everything you've written in a blog, it's all there. And then they use vast statistical models, which we were hearing about yesterday from Mira, to predict the next word or the next string of text, based on analysing web documents. And, well, there's a huge quantity of discussion about all this. What can go wrong? Well, they can display bias, obviously, garbage in, garbage out. You know, it's only based on what they've ingested. One of the things they haven't ingested, they've ingested lots of mathematical papers, but all that informal stuff, all those things about what are we doing when we stand around the blackboard and try and convince a friend of that's not there. That's not available as text on the web for them to ingest. There are lots of gaps. It hallucinates, which is the posh name for making things up. And, you know, you can sort of see why. You know, it's seen as a connection between Max Newman and Turing, and it's desperate to bring Turing into the conversation, like a very enthusiastic and rather bad student. But what don't they do? Well, they don't recognize error. They've got nothing against which to calibrate error. You know, if there are some sources that say the moon is made of green cheese, then just occasionally it'll tell you the moon is made of green cheese. It doesn't recognize it's stuck. So it's sort of, well, how can I make a connection with Max Newman? I don't know, with Turing. Oh, I don't know, it must have been Turing machines. And it's not actually replicable, you know, so it'll give you one bunch of stuff today and then another bunch of stuff, you know. If you try this experiment again, it'll give you some other result, maybe even right. Well, as I said, large language models for math are at the root of what's going on in OpenAI. And fortunately for me, Michael, who is here somewhere. Oh, hello, Michael. Michael is going to tell you a bit more about some of this later today. But essentially, what they've done is they've ingested vast volumes of math-related documents. They've also ingested mathematical problems with solutions of various kinds. And perhaps the best way to think of this is, if you think about something like a mathematical proof or a chess game or a Go game, unlike a chunk of text, there's a right answer. You can tell if the chess game is a checkmate position. You can tell if the Go game is a one position. And that means not only can you give it a collection of right answers to train on, you can generate millions and millions of more correct Go games. And then that's what they did with AlphaGo. They generated millions and millions more Go games and used that to learn tactics of playing Go. And similarly for alpha geometry and alpha proof. So there are the stuff at the front, who knows what garbage it is, technical term. The stuff in the middle, you know, can be sound, one hopes is sound. And then it goes on and comes up with solutions. And that's the kind of thing that's going on in OpenAI's O3. This diagram comes from, it's a hugely fast-moving field. This diagram comes from a paper by Yang et al. From 2024 called AI for Maths. The paper is about 10 pages and it's got 290 references. And this work, there's huge volumes of stuff being done and published not in math journals, but in computer science journals, AI journals, and so on. So when we go back to this, what's happening here? Well, OpenAI are using these people's names to legitimize or validate what they're doing. OpenAI have clearly done something that's a bit dodgy. The conversation, of course, the original question that we were being asked by the AMS was, well, what about doing all this, you know, what's the impact going to be on mathematics? Well, if you start looking at this in terms of this model here, well, there's all kinds of questions you can ask. I mean, anybody who's a journal editor has already seen it manifesting itself with spam papers generated by AI. And, you know, the world out there isn't necessarily going to wait for the AMS to write a policy document. You know, the world out there is just seeing what it can do with this stuff. But of course, one of the challenges is, if you look at this nice, neat, tidy model, all this stuff down here, accountability, governance. You know, having releasing your product with a press release with a few quotes from a Fields Medal winner is not governance. Governance is having somebody who's actually accountable for this. The AI companies, well, they're putting a lot of investment into this at the moment. What's to stop them pulling it? Just like Microsoft pulled their version of Google Scholar. And one can ask the question, what are they getting out of it? What is OpenAI getting out of this? Now, OpenAI employs a lot of very sharp mathematicians who are doing incredibly clever stuff. And so one wouldn't diss the quality of the technical work. But as a company, how is this adding shareholder value? Well, maybe they've got what they wanted out of it. You know, it won a competition, you know, a bit dubious, but it won a competition. It's been endorsed by some big names. Now, why? Why would an AI company want all that? Might it be pitching for the next big opportunity? This is this is a presidential action from the White House last week, April the 23rd, 2025, improving education from AI. The gist of it is that the NSF will skew its priorities towards this sort of thing. There's going to be lots of government money to invest in private companies to deliver AI. You know, that's what they're up to. So how would we answer this question? I mean, apart from picking apart, you know, their use of the English language. But, well, first of all, this is a huge technical accomplishment. I mean, you know, you look at the things that this stuff can do. AI plus computational logic can do incredible things. It can do weird things like flooding the market with spam math papers. If you wanted to embed it in mathematical practice, even if you wanted to just do one of the things mentioned in the paper from Epoch AI, like help with referee, you want to think very clearly about how you're going to do that. What's the infrastructure? Where's the accountability going to be? Or not, you would just want to let it rip, but you might, if you weren't choosing to do all that detailed work, you might want to stop and think why you weren't. There's a balance here. I mean, in fact, that's why I started the story in 1946. There's always been this balance between big tech, government, and the mathematical community. The mathematical community, Michael's written about this with reference to the NSF. The mathematical community, you know, uses the big tech to solve the problems it wants to solve. But you know, the big tech's payback is that big tech can then claim the endorsement of the mathematical community. When you look at these discussions, one thing that really strikes me is how very Anglophone and very US-centric they are. So this paper had, I think, 6 or 8 authors, 2 from Toronto, 2 from Canada, and the other 6 were from the US. You know, several fields, other fields medalists are available. If you start looking, and this seems to be very much a US-driven debate about what is AI going to do for mathematics. If you look at other websites of other learned societies, the French Mathematical Learned Society, unless I have totally mistranslated artificial intelligence into French, doesn't have much reference to any of this sort of thing. The German mathematical societies have an announcement. It's the other way around. It's the kind of PR we were hearing about yesterday. It's a very nicely written document about the importance of mathematics for advances in AI, the importance of serious mathematics in advances for AI. You look at the IMU, and there's really a rather embarrassing, very dead web page for the Committee on something or other, digital something or other, which was last updated in 2021. So it doesn't look as if they're part of the conversation. And the other point I would make, I think, is that this is actually bigger than mathematics. How could anything be bigger than mathematics? But it is, because actually what we're getting into is the politics of AI. And there are discussions happening all over the place about the politics of AI, sometimes hiding under phrases like governance or ethics, but there are big discussions about where AI is going and how not just individuals or institutions, but on a national basis, might be national engagement. One of the last acts of our former Prime Minister, Rishi Sunak, was to hold an international AI summit at Bletchley Park with the usual sort of cliche-ridden press releases and so on, but he brought big names together to discuss it. The next one was scheduled to happen in Paris, by which time we had a different Prime Minister who was trying to walk away very fast from the Rishi Sunak legacy. And the US sent their Vice President, who said lots of interesting and controversial things, most of them nothing to do with AI. But if you actually look at what came out of that, it's very interesting. This was about a commitment to what's called sovereign AI, AI capabilities that were separate from what was happening in China. I haven't even mentioned DeepSeek, which is China's answer to OpenAI, separate from what was happening in the US. The idea that there could be a federation involving the EU, India, to pull together their own kind of sovereign AI based on. I've sort of skipped past it. There have been huge international contributions from many places to the research work I'm talking about. It's just the public presentation tends to be very Anglophone-centric. Oh my lord, I've left 16 seconds for questions. Sorry about that.
So thank you so much. Unfortunately, we have 3 seconds for questions, but I was chairing this session. I hope you will understand that I didn't want to stop Ursula from. It's such a privilege to have a scientist of your caliber to think about these matters that are of great interest for us. So I didn't want to interrupt you because it has been a great pleasure, and we will discuss this, later in the corridors and.
Well, I should have interrupted myself, because one of the things that comes with having lots and lots of lectures in one's life, especially with huge big numbers up there like that, is it's actually just a bit incompetent.
But, indeed, it has been a terrific talk. Thank you so much, Ursula. Thank you.